Hi guys, and welcome to this Wintellect webinar, Microservices on Azure. We're going to be talking about serverless containers and a lot of other things today. So a little bit about who I am. I'm Blaze Stewart. I'm architect at Wintellect, which is now part of Atmosera, and we are glad to have partnered with them, with Atmosera folks now, and big happy family, and doing MSP stuff as well as consulting and training, which this is part of that as well. So let's go ahead and just give you a brief rundown of Wintellect and who we are. Let's get this up there. And so Wintellect, we are a company that combines training as well as consulting services, and now with Atmosera, hosting services for different services related to Microsoft Azure. So we are very focused on the Microsoft space and the consulting space. We do a lot of architecture, analysis, design work, and development, and different kinds of things related to application development, as well as moving workloads onto Azure. And then the training space, we kind of reflect that with training on Azure, as well as software development and a lot of other realms as well. So we're a full shop, so we do just about everything you can possibly think of in the Azure space. So enough about that. Let's go ahead and let's start talking a little bit about what we're going to be talking about today. Now, of course, the topic of conversation for today is microservices. And I wanted to talk about microservices in general, just to kind of frame this discussion. I mean, there's a lot of, I don't know what else to call it, but there's a lot of differing opinions on what a microservice is, what composes a microservice, what are the characteristics of it. And I'm, excuse me, clear my throat there. But in short, a microservice is simply just a service that does one thing. And it, generally speaking, it is going to be a service that does some unit of functionality that's part of a suite of other services. And so up here, we might have a front-end web service that its purpose is to receive calls from HTTP clients. And then it might have some back-end services right here that do other things related to processing the data. And this might have reliances on other services that do things like specific functionalities like send emails or do things like that. So all of these different services are basically doing a single piece of an entire suite of services that formulate an app. And these services together are what we would call our application, rather than a single service representing an entire application or something like that, which we've traditionally called a monolith. And we have inside of our application of, or really our suite of microservices, tiers like we would have in a monolithic tier application. The tiers don't go away. We just decouple the services from one another, and we use network protocols for those to communicate. Now that network protocol could be HTTP based, it could be message buses, it could be any kind of messaging platform. Regardless of what that is, it's basically allowing for a service to communicate with another service by way of some network protocol, so that these services can reside on any number of different compute nodes or different kind of compute platforms, even depending on how the application is constructed. So the bottom line with microservices is that you self-contain a piece of functionality, and you do that in such a way that it can operate autonomously from the rest of the suite of microservices, and it uses a network to communicate. And that's fundamentally what makes a microservice a microservice. That has huge implications, and that's what I want to talk about at the kind of out of the outset here. And I wanted to frame this around challenges that microservices face, and then we're going to look at the different technologies, including serverless on Azure, as well as containers on Azure, and mention a few other ones that will perform microservices, but talk about the points of contention and the advantages of doing microservices using those platforms. So the challenges are really going to be the questions that people will ask when you deploy microservice. How do I do this? How do I do that? What's the best practice for X, Y, or Z? And that's really what we're trying to get at with the challenges. If you were on our last webinar, I did go over these challenges. So I'm going to go through these quicker than I did last time, just to frame the discussion, but I do want to get through these just so that you have some context when I get to talking about the actual platforms. So challenge number one is state. And there's several ways to maintain state. Because services are decoupled from one another, everything's running kind of autonomously. State is not contained within any single service. Rather, a service might need to interpret or get state from somewhere else. It might need to offload state to somewhere else. And you cannot count on a given service having the state for every other service in the microservice suite unless you're using a cache, of course. But the point of doing a state management is so that you can centralize or at least distribute the state and make it accessible to everything if a state is needed in a service. Generally, the best practice is not to have state in your application to the degree possible within your services, but inevitably that's almost not possible in a lot of applications, but you can do it. One way is to push that up to the client, and the client sends everything it needs to the services to fulfill the request for a given request that's being made for a given piece of functionality in the service. Now that could be just making a request to get data, it could be saying process something, but it sends everything that is needed to process that request. Now, another common way to do state is to use sticky sessions and use a load balancer to do that. What ends up happening there is when the clients connect, everything, when that client first connects, it's assigned essentially a token, and then every time that client connects again for every subsequent request, it sends that token. Typically, it's some kind of cookie or some kind of token that's attached to a message, whatever it might be. And then that way the load balancer knows where to send that particular request, and so that whatever connection that is coming in from that client always hits the same backend service. Now that's fragile. It doesn't, it creates single points of failure. So if a node fails like this one here, all the state for a given client is lost because it's maintained in the memory. Now, typically what is done inside of state management is a distributed cache system like Redis. And then what ends up happening is all the state for every service, if it needs it, is stored in that centralized repository, and that is highly available, etc. It's usually spread across multiple nodes to make sure that it's redundancy baked in, so there's no single point of failure in the cache itself. But then every time a new request comes in, any service can handle that request, but it just goes to the caching service to get whatever state was needed for that request. It loads that state, and then it's available for that particular request to process. Now, the Redis cache or whatever is fulfilling that, memcached or something like that, will have some kind of cleanup process to get rid of stale sessions and that kind of thing. But all in all, state is one of those things that has to be maintained. Challenge number two is configuration management. Now, configuration management is one of those things that you have to do to get the configuration right for a service. And this is impossible to do at scale manually. So you automate it to the degree possible. One common way is just to create a configuration service. This is popular in the Spring framework with something like Eureka. And basically what you have is a configuration service where every state that starts up knows that configuration service's endpoint, and it says, here I am, what's my configuration? And then the configuration service sends back some kind of configuration payload, and then the service configures itself and it knows how to reach databases, etc. Another way to do it, a common way to do it, is using platform storage. And this is what you typically do in a containerized application. You would basically store some kind of configuration on a platform storage. It could be through secrets, it could be through a mount into containers or something like that. And the services that are running on that platform can all access that storage, and they read in the configuration data from that, and then they can then read that configuration information and configure themselves accordingly. Another way is to do it through DevOps, and that's basically where you inject all the settings whenever you deploy the service. And so the settings are stored inside the DevOps operations suite, tool, whatever that might be. And then whenever the DevOps process runs, it takes those settings and merges those with the deployment packages, and then sends those out to the production or the staging environment with the settings as part of the deployed package. And then the services come up with that configuration data already there. So 3 possible ways. Typically, the way it's handled in most cases is using some kind of platform storage, and with a second alternative being configuration services. However, DevOps is becoming a more common approach for doing that, so that you can have multiple environments doing a lot of different things, as well as centralizing those stored variables and things like that in the DevOps settings. And sometimes it's a combination of these. So challenge number 3 is service discovery. Now, configuration is part of this, so these two kind of go together. Challenge 3 works a lot of the same way, where you have, and where whenever another service is trying to find a backend service, how does it do that? One of the most common ways nowadays, especially with serverless and containers, is using just a load balancer. And the load balancer is what we call a well-known endpoint. It's basically a host name that this guy knows, and it doesn't need to know the backend addresses of each of these, or the names of these backend services that this is load balancing. And so what this does is it just goes to this endpoint that is a load balancer, and then it will delegate the load to whatever the backend services might be. And this is typically DNS-based or name-based resolution, and it works really well. And Kubernetes has a lot of built-in functionality for this, and it's very common for other approaches, let's just serverless, to use this as well. Another way is to use a discovery service, similar to configuration. It works works the same way, but instead of having a baked configuration management, basically when a new service comes up, it notifies the discovery service that I've come up. And then whenever a request comes in, it says, I need an endpoint for service type X, Y, or Z. The discovery service will then return the endpoint for that service, and then it can make the request to that service like it would if you were, if it already knew it. But it works a lot of the same way that DNS does, except it's doing it in a more high-level way rather than relying on network-level protocols to handle that. Either way works. This one is probably preferred in a lot of contexts because it's very simple using existing technologies. Excuse me. And then this one is a common in suites where there needs to be some kind of monitoring involved, where you don't want to use a lot of load balancers and things like that. And it's come out of the Spring framework, which is really taking that to the next level with something like Eureka. And challenge number 4 is interservice communication. Now, interservice communication is a challenge in any system. Of the challenges, this is probably one of the biggest ones, and it's trying to figure out, how do I get my services to talk to one another? And one common approach is just to make everything an HTTP endpoint, and that would be what we might call a synchronous pattern. And basically, that's where every service has an HTTP endpoint, and it makes requests to other services by way of the HTTP-based protocols. And this is synchronous in that it's not so much synchronous code, but it's a synchronous request. I send a request, I expect a response back. That is a pattern. It works for the most part, and it's been widely used in microservices. However, increasingly, more and more folks are moving to an asynchronous pattern using messaging platforms like message buses and such as MQTT or AMQP protocols, or something like Azure Service Bus or other similar messaging platforms. And they use something like a topic, which uses a one-to-many type distribution of messages, so that whenever a request comes in, it basically sends a request to a backend service by queuing it up on a topic, and then that topic will then send a copy to everybody that is subscribed to that topic, and then everybody on the backend processes it. Or you can do one-to-one through a queue, which allows multiple front ends to publish to that queue, and then there are multiple iterators on the back end that might be listening on that queue to read those messages off the queue and then process them. And this is asynchronous in that this right here is not expecting a response back from whatever process is in the back end. Now, it is possible to have a feedback loop if you wanted to have another queue for responses, and you can use something like a correlation ID between the original message for requesting something and then a response that comes off the queue, a response queue, and use a correlation ID to get responses and requests correlated together. And that's a common way to do that, but it's asynchronous in that the actual request onto the topic or the queue is not expecting a response back immediately like you would get with HTTP-based protocols. Now, this one is generally considered to be a better practice in microservices because it does scale better, and it also allows you to have a decoupling between your backends and your front-end services, your backend services, and things like that. And it allows you to take a service offline for a while and just build the queue up, upgrade it, and then turn it back on and start reprocessing it. And and it also works better for creating things like circuit breakers and things like that, because you don't have cascading failure in the event that you have a bunch of synchronous requests that are just building up and requiring request, response in a chain. This allows you to decouple things in such a way that you don't have that kind of build up, so you can have cascading failure in that respect. So asynchronous is generally preferable, but synchronous is still acceptable in some contexts, and a lot of people still use it. So the next challenge is security. Now, the security aspects of the microservices, it comes down to two basic premises. One of them is considered trusted services. The other one is considered zero trust services. Now, trusted services has been the bulwark of what we've done in the past with microservices. And the thinking here is you secure the perimeter, and everything else inside of the perimeter is considered a trusted request. So if this service on the edge validates the request coming in from my client, then it can forward that request into a backend service. And this backend service does no validation of that request. It just assumes that the request has been validated by something on the edge rather than validating it internally. And this is considered a trusted microservice suite here. Now, this is obviously less secure because if somebody can compromise the perimeter, they can inject bad code into the actual suite, and then they can access other services without authentication. And so they can possibly get a bunch of data and then offload it to an external system without ever doing some authentication and circumventing any security measures that might be in place. So zero trust basically discards the idea of perimeter security and just assumes that nothing is secure regardless of where it came from. So if a client makes a request, then the edge services that are receiving that from the client validate the request. If it makes a call back to a backend service, that backend service again validates the same request. It might use the same token, it might use the same, it might use a different token, it might use a different mechanism for validating the request. But all in all, what it's doing is making sure that this service right here is presenting credentials with the request that this service will recognize and therefore will validate against either some kind of centralized identity management. It could be PKI with public key infrastructure where it's using certificates, and it could be doing any number of schemes. But the basic thinking there is that every request, regardless of where it came from, does a validation against that request before it processes it, and then it rejects the request if the validation fails. And so there's a number of ways again to do that, but the bottom line is you assume nothing is trusted. You just have zero trust until you have that validation happen. And lastly, challenge number six is data access, and that is dealing with how data is accessed. Now, I present the CAP theorem here because this is oftentimes where a lot of folks kind of get wrapped around the axle with dealing with a particular request and dealing with data. Now, if you've worked in IT long enough and you're a developer, you're probably used to data access being what we call highly consistent and highly available. And so it's basically looking for something right here. So the CAP theorem basically says you prefer two of these three different kinds of ideas. So consistency basically means that your data is consistent across all nodes when the data is written. So that's what we call strong consistency. And so that means as soon as I write something, every subsequent read of that same record will be exactly as I wrote it. Now, weaker consistency models don't guarantee that. They basically say, If I write something, the next person to read that data might not read my writes until my writes have propagated across all of the nodes in my data system. And that is what we call weak consistency. The reason that we do things like weak consistency is to provide fault tolerance and partition tolerance so that that we can have data that is available and partition tolerant while sacrificing consistency in that respect. And that is basically enabling me to distribute my data across wide geographies and across multiple nodes that will ensure that my data is eventually consistent, meaning that the writes will eventually propagate, but it means that if my data nodes go down or my partitions go down, I can at least still operate with a given subset of my data. And so this makes my data systems more highly available. Now, traditional databases have done a lot with strong consistency. That's this one right here, and strong availability. And that works great if you're working on a local area network. You have 5 high-speed data connections between various nodes. However, again, if you're running across multiple regions and you want to be able to have a data system, that doesn't work well because you have latency issues. You have networking issues that could potentially disrupt data replication, and that could really make things really nasty for a database and bringing the whole thing down. So that's really what Mongo and Redis have generally preferred, and it's also what something like Azure Cosmos DB prefers, in that it prefers availability and partition tolerance over data consistency. Now, you can do data consistency in something like Cosmos, but you do so at the expense of availability. And the availability, that means that you can only write to a single region in that respect. And so that is just the trade-offs you make. So generally speaking, for microservices, it's to prefer these down here with availability and partition tolerance. And so the data access modes that we do that through are either direct or indirect. And the reason why I want to present this is to show you the way that data is accessed. Generally speaking, this is considered an anti-pattern inside of microservices, where you have your microservices actually all directly accessing data using a more synchronous mode. And the reason why is that this mode generally assumes that what you have is strong consistency and strong availability. Now, that has been a pattern that has been implemented in the past, but as a rule, it's generally considered a bad practice in highly scalable microservices. Rather, it prefers indirect access through a data service that is brokering data access to a database. So what you end up doing is you write a data access service that other services then call, and then that data service then is the one that's going to broker data access for this. And there's also a lot of other trade-offs for this. This is generally going to be better, more secure, because you have data credentials only in a single data service, rather than trying to configure all your different services for every possible database that they might use. And this is also going to restrict the number of connections into a database. It's also going to do better management of those connections as well. And so this will allow you to have a single point of entry into a given database. Now, of course, this is going to be highly available, etc., but it's going to be better than having every single every single service accessing a general a database directly, rather than through a data access service. And the other reason that you want to do this is for this right here, and that is to implement a CQRS pattern. This is the one that has traditionally been done with a lot of data access microservices. It does CRUD operations, create, read, updates, and deletes. Again, strong consistency and strong availability for data. Now, this works well if you have a local area network and you're running your data base on the same network, basically, that your access, your APIs or your microservices are running, but it's synchronous and all that, and it might work well for that, but it doesn't really scale well to multi-region and or even large data center access. Instead, what we preferred is a CQRS pattern, which is kind of an alternative to CRUD in that it really gets to an asynchronous model for doing data access. And what this does is it separates reads and writes from one another. So over here on the left, we do all of our writes. So this is our creates, updates, and deletes other type of write access. And then those go down into a repository pattern, and those actually do a those actually write to a write optimized database. And then when writes happen, it does also notifications of that particular write, that data has changed. Then in the back channel, there's usually a data sync process between a write optimized database and a read optimized databases. And this might also include some kind of data transforms to take data out of the form that exists here in a write optimized form into a read optimized form. So maybe it's some data denormalization, maybe it's doing something else that makes it more optimized for high performance reads. And then when data is read, then data is read out of this database. And also you have this event handler loop right here that can also bubble up events to people that are listening, to clients that are listening for data changes on the read side. So this is not only performing queries into the data, it's also notifying clients when data has changed. And so they get notified when a particular piece of data is changed. So it's using some kind of messaging platform to handle that. So this pattern really does work well for scaling out your microservices for data access in the back for backend services. Now, it's again, this is much more complicated to implement than CRUD, but this is also going to scale a lot better because it gives you the ability to distribute data and then also treat your data in an asynchronous model. So the takeaway from data access is primarily getting at get your data into a point where you can access that data and treat that data asynchronously rather than relying on strong consistency and strong availability. If you can go to a more asynchronous model and then have an asynchronous data model for your database as well, you can build a CQRS pattern, and then that will basically give you the ability to have highly scalable databases that will match your highly scalable microservices to boot. So you have these two going together. So that's kind of the trade-off between these two, is the synchronous and asynchronous approach. So that's the 6 challenges. So I want to talk now about the technology, and that's really where we're going to spend the rest of this webinar. And so the idea here is to get into the particular technology stacks on Azure and look at those and how they will answer a lot of these challenges for data access, for security, and so on, for doing a lot of these various kinds of challenges that are faced that you face whenever you do microservices. And again, microservices being a pattern, not so much a technology, there's a lot of ways to do microservices at the technical level, and that's where we're really trying to get at with this webinar. So the first one I want to talk about is Azure Functions, and this is Azure's serverless model. If you're not familiar with a function, it's basically a programming model that allows you to use serverless, that means programming models, to get a particular application running. Now, the way that serverless works is that you have a model that is presented to you in your IDE, in your programming platform, whatever it might be. You basically, as a developer, focus on the code and you implement bindings that feed data into your code and then have output bindings for things that are outputs from your code. And then this provides a nice abstraction layer between your code and the underlying platform, so that all you really need to do is focus on the code that is being implemented in your particular function and let the actual platform handle all of the other things that we have to talk about. And because of that abstraction, you don't really have to focus on things like implementing the HTTP protocol or being context aware of the HTTP protocol. Everything is presented to the actual function as an object. You don't have to write code to handle the HTTP protocol, or you don't have to have specialized controllers or specialized frameworks, any of that. You don't have to deploy a web server. You just do the code, and then you can then implement HTTP endpoints in the same way that you would probably implement something like something that's listening to a service bus, or something that's listening to some kind of other type of storage, like blob storage on Azure, whatever it might be. They're all event-driven methods of getting data, but to the programmer, it doesn't really care. It's just, here's my binding, where's my input? And then it gets that input, and then it processes it, and then does some sort of output. So one thing I love about the Azure Functions is when we talk about scaling, I didn't particularly talk about these from a um, a high availability perspective, but this does relate to state management and that kind of thing. Scaling and high availability, which are obviously challenges that microservices face. They're challenges that I didn't specifically address, but the scaling and high availability for functions is provided by the platform itself. So Azure App Services, which underlies Azure Functions, does this out of the box. You don't have to configure anything. State management for Azure Functions is generally not baked into the platform. So if you want to do state management inside of Azure Functions, you would need to implement that in some way. So either have a state service, so you might have a state management system such as Redis running on Azure. You can do that with Azure Redis, and then you can read and write state from that in your functions if you need state. And there is some level of statefulness with durable functions. However, you can't count on durability to maintain state. Any session state that you might need to maintain needs to be either needs to be passed as part of the request or needs to be maintained externally by some kind of caching service. Durability is basically there to make sure that the function is orchestration. The function orchestration is happening with other subsequent calls that might be made from one function to another, or external services or something like that. But it's really not something that you want to rely on for maintaining any kind of state with your application. So you want to make sure that you get any kind of application specific state out of your functions and make sure that is maintained externally. Configuration management for apps of Azure Functions, again, is generally self-configured from settings. So this would be a platform feature. You can read settings out of the configuration, and then that will be presented to your application. It's something that you would basically either configure through DevOps or manually do it, but generally DevOps is going to be the way to handle that, and then you would inject the configuration as part of your DevOps deployment, and then you can read that whenever the service starts, and it will know, connection strings, that kind of thing, if it needs to access data. It might have other types of configuration data for accessing external APIs and those kinds of things that you might need for configuration management. So that's definitely going to be part of the platform itself. Service discovery is not built into functions either. Generally, service discovery is handled through DNS and well-known hosts. That's the thing about Azure Functions, is because these guys scale well built into the platform, you don't really have to think about implementing that manually. All you really have to know is where's the endpoint, and the endpoint then will be exposed to whatever's calling that backend service or whatever it might, even if it's a front end service, and you don't have to worry about the load balancing, the high availability, or finding or doing service discovery for any particular node. You just say, here's the well-known endpoint, and then you pass a request, and then the internal mechanisms of the platform will then do the load balancing for you. Now, the one thing I also love about Azure Functions and the serverless model in general is the way that it decouples service communications from the actual code that you're doing. And it really depends on the serverless bindings to maintain that. So the inputs and outputs from any Azure function is really going to focus on what is coming in through the binding and what's going to be output, what's the output from the binding. It can be HTTP request, it can be putting a message on a queue or something like that, but the bindings really handle that. And they are adapted, can generally be adapted for synchronous, but asynchronous is generally going to be the best way to go with Azure Functions, is to use the asynchronous patterns there. I really like to build Azure Functions to have a front-end API that basically uses HTTP-based bindings, and then use Azure Service Bus as a backend. So basically, what you do is you have an Azure function receives a request. It takes the request, puts it onto a message on the message bus, and then it returns a response back to the client saying, "Hey, I unqueued the request. Here's the correlation ID for this request. If you want to," and then what you can have is another API endpoint that has a status check. saying, what's the status of this request? And then you can pull it, or you can also implement something like WebSockets, and then have the request listen, have another function that's listening to a service bus, and then you can do WebSockets that allow it to publish something back through that service bus that will listen to that and to the request, and it will then on cue that response back to the client, and then the client will receive that and be able to correlate things using correlation IDs. So Interservice Communication is one of the places where Azure Functions really shines as well. Security is really a good thing with Azure. Azure Functions has really good security when it comes to what I might call bolt-on security. There's no inherent security to the platform other than like API keys, but you can, that's what I call bolt-on security. So there's no like built-in security for HTTP-based bindings, for instance, or there's no for output bindings. But what you can do with the security built into Azure Functions is use the built-in at the function level. You can have keys that are used for requesting data from those, and you can use that as bolt-on security. Another thing you can do with functions is you can front end it with something like APIM, Azure APIM, that's API management. And what that allows you to do is have API keys that you can use in front of Azure Functions. And that's a way that you can do bolt-on security through other service authentication and so on. So those are different ways you can handle the security going into the Azure Functions on the perimeter. Now, internally, there really isn't any internal security unless you're using unless you're using the service keys. And so that would be a way to do inter-service communication authentication. If you want to have a service call another service, is to turn on the keys and then for a function, and then have that key presented with every function call, and it will validate it. So that's what I might call bolt-on options for that. Now, versioning, I didn't cover versioning, but versioning there is as a challenge, but there's no inherent versioning, but that is something that would have to be addressed so you can upgrade these whenever they happen. Data access, Serverless prefers asynchronous data access through external data access, and I would encourage you to adopt that as a pattern if you're going to go with functions anyway. And that's to use asynchronous inter-service communications through something like a CQRS pattern, and then implement data access services that will have the ability to read and write data using the CQRS pattern and make that data access asynchronous, and then have the data access asynchronous and the inter-service communication asynchronous, so everything is asynchronous. And that way you can have full feedback loops and do that in an asynchronous manner, so you don't have cascading failures and so on, that are typically one of those things that microservices can really suffer from in the event that there's a node failure or node outage somewhere on the microservice suite. Now, I wanted to show you an example of a microservice. I built a small one just to show you kind of what this looks like. So if I was going to present this, let me go back over here and pull up my code here. I have a small service here, and it's basically a function app, and this is a small microservice here. And this, just to show you what a service looks like, it has a set of APIs. It's got an API service. This is an HTTP based service. And basically what I can do with this service is add, subtract, multiply, and divide. And this would be a small autonomous service that has a couple of different methods that you can call on it that would be used for some kind of functionality. Of course, this is a trivial example, but in this example, what I can do then is deploy this as an Azure function. And what this allows me to do is have a very self-contained, very scalable application or service that I can scale out rapidly using Azure Functions. Now, if I was going to do this inside of a command prompt, let me get over here to my code, and I'm going to go cd source and microservices/FA. Now, if I wanted to run this on Azure Functions, I have this in a development environment right now. I can do func start. And what this will do is allow me to run this locally. And you can see here I have the API like this. And so this particular service would be a serverless service, and I have deployed it using HTTP-based bindings. Now, the bindings look like this. Inside of my code, I've just defined a simple input-output binding that looks like this. And this is my input binding right here. And I have the authentication level turned on as function. Now I can, if I wanted to make that anonymous, I could do that. And that would make it anonymous if I wanted to do that. And I think it's probably going to give me an error if I try to access this. Maybe if I had that function, if I have this configured right. Let's see. Let's take this right here, copy it, and then let's open up a new browser window here. And let's see what happens if I paste this in. And let's see if okay, so it's allowed me to access it anonymously. The one I have running, I had some old code in the code editor there. And this one is basically just adding two numbers together. So if I change that to 4, I get 1 plus A plus B equals, you know, whatever the value for A, whatever the power value for B is, I add those together and I get, you know, the sum. And I can do the same thing for, let's say multiply, and multiply 1 times 4, I get 4. And so I have this small API that's basically scaling out or accessible through an API endpoint. Now I deploy this to Azure using a function app. Now let me pull my Azure instance over here. So my Azure instance here, I have a function app deployed, and that's my Kubernetes. I'll be looking at that in a minute. I have this function app deployed, and it's pretty straightforward. I basically took that code, deployed it up to a function app, and you can see here that I have the same four methods deployed in a function app here. And this would be my endpoint for my application here if I wanted to go into my API right here. So if I wanted to get this particular one, I can do, since I already have run this, I can see that I'm adding I'm calling an API endpoint. And this would be my well-known host. It would be blazemicro.azurewebsite.net/API/add. And that's my well-known host that I could call from any other service. And then the platform is going to do all of those things that I just talked about, from scaling to configuration to all of the various things that I'm going to be doing inside the platform. Now my code is very basic. I didn't have to configure any websites. I didn't have to configure any kind of HTTP bindings. I'm sorry, any HTTP protocols in my code. It's all managed by the platform, and this just allows me to write very simple code, and it handles my code for me. It's stateless, it's got all those things. And so this would scale very well using a microservice pattern using serverless technology on Azure. So the serverless approach is a very viable option for doing microservices. And it's one that if I was approaching something greenfield, I would definitely consider this one probably as a first choice because of its ability to take a lot of the headaches of managing a lot of that infrastructure away from me, and I just focus on writing code, and I'm really ready to go. The trade-off being that I have to adopt the patterns and principles that this particular implementation of serverless provides to me. So I can't just take my Azure function and take it over to AWS and run it in Lambdas. And so I'm going to be essentially running this on Azure if I adopt Azure Functions as my serverless platform. So let's talk about the next option, which is going to be containers. Now, containers are obviously going to be very versatile, and I'm going to approach this from the perspective of Kubernetes. The containers are very versatile in what they can run, but given that containers out of their inception were really kind of a way to do microservices. Of course, they've taken on a life of their own. They can do a lot of different kinds of things. That one of the primary use cases when the container movement really started about 5 years ago was microservices, and it was really trying to come up with a way to create a platform that would provide me with the ability to write all these small autonomous services and deploy them at scale and create me a management system that would manage them at scale. And that's really what birthed the container movement, and as well as container orchestration. And Kubernetes was kind of a late in the game. Swarm was kind of the first attempt at that, but Kubernetes has really risen to the top as the way to do that in the container space. Of course, you can still do it other ways, but Azure Kubernetes Services is the Azure implementation of Kubernetes. And for that reason, Kubernetes does a fantastic job because of managing things for microservices, because it just has a lot of the built-in plumbing to support microservice architecture. But because it is what I might call a little closer to the metal, a lot more of the responsibility for configuration falls to the user, the developer, but it gives you a lot more versatility. And so it's going to be one of those things that you kind of have to choose. Well, if functions doesn't do it for me, maybe I can do it with something like containers. Or if you have an existing application and you want to make it more microservice oriented, sometimes getting into a Kubernetes environment by breaking up a monolith into microservices gets you a little bit more closer to that, because you don't have to do a lot of refactoring for services to work there. Rather, you containerize them, then you take advantage of the platform itself to get you a lot of the features available. So one of the things that Kubernetes does well from a scaling and hybrid high availability perspective is that it just creates a bunch of nodes, and then it scales your application across the available nodes based on how you on desired state of configuration. And so that's going to give you, that's built right into the platform. High availability, again, is built right into the platform. And so it's fault tolerance in that if a node goes down, Kubernetes attempts to move work around to healthy nodes in order to make sure that applications are running in a way that is going to be according to the desired state configured by whatever method you use to configure it. State management is not something that's built into the platform, but so you generally have to bring in something to do that. So there's no baked-in state management for Kubernetes. You would have to bring it in as something like a Redis as a containerized instance, or use it if you're running Azure Kubernetes services. You could adopt Redis as a service, Redis platform as a service offerings on Azure to provide you some of that caching services. But you can also containerize a caching service and provide state management and go with that option as well. Another thing I love about Kubernetes is its ability to do configuration management built into the platform. Kubernetes provides configuration management through a lot of different means. It does Kubernetes secrets are a good way to do that. It integrates with Azure Key Vault, so you can store secrets in Key Vault that act as configuration settings for things like connection strings and secrets like API keys and things like that. You can use Key Vault as part of that configuration management. And you can also use shares. So if you want to do mounts inside of your containers using shares, you can have configuration settings stored on shares. I wouldn't do that for things that you care about that are secure, but I would definitely use secrets or use Key Vault to manage secrets. And then you can use Kubernetes integration with that to get those secrets out of Key Vault and use them to configure your services. And another good way to do this is through secrets management and through DevOps. You can do it through config maps with DevOps practices, or you can use scripts. Another way you can use this, you can also do this with Helm, which is a third-party tool that integrates with Kubernetes that allows you to have configurable packages that you can deploy using Helm charts. And so there's a lot of ways to do this with Kubernetes. I generally like to use secrets and then if I need to do some kind of specific environmental configuration, such as well-known endpoints, I'll use config maps or Helm charts to do that. So generally kind of a combination of the two. Service discovery, again, Kubernetes has got this built-in do ingress controllers or load balancers. It's got internal load balancers and ingress controllers, and you can configure well-known endpoints within the container cluster itself. That's very easy to configure with Kubernetes. Not a lot of stuff you have to do to configure that out of the box. It just works, and you can use DNS-based service configuration there. Interservice communication on Kubernetes can be a little bit trickier though. And I'm gonna combine this one with security, because Kubernetes provides integrated contiguous networking across the platform, so you don't have to worry about configuring the network layer but it does not provide any built-in like HTTP encrypted channels that are inherently secure. I mean, the data is encrypted at the network layer, but if you had a rogue container running in the platform, it would still be able to read that data, and it would still be able to read that data in clear text, just like any other container running in that platform, even though the network itself might be running in a secure, the pipe itself might be encrypted. But there are some third-party services that you can add on to the microservice suites, such as Istio. And Istio is a service mesh, and Istio gives you the ability to provide what we call a proxy sidecar container that will encrypt traffic, and you can configure that to accept only traffic from specific or trusted endpoints to get you a zero trust configuration using a service mesh. Now, that's not built into the platform, but it can be configured using some third-party tools like Istio or other service mesh implementations. Now, Istio is kind of the one that most people prefer because it's kind of gotten the most traction. However, there's Console, there's other ones. I'm drawing a blank on some of the other ones, but their Console's another one that comes to mind. And then I think there's one from, I'm drawing a blank, doesn't matter. Istio is probably the one that you want to use anyway. Versioning with Kubernetes is also very easy to do. It provides specialized controllers for doing rollouts of new services, and it has rollback options as well. And then database access with Kubernetes is something that you would have to build into the application service layers. It's not something that it provides out of the box. So this would have to be something that you would have to build into your microservices. You would have to basically create a microservice that provides a data access layer for your services and how they run accordingly. So Kubernetes, again, is one of those, it's a Swiss Army knife, a lot of built-in functionality for microservice architecture. And if you're thinking about going about migrating an application into from a monolith into a microservice architecture, containers provide a way to get your application into an environment that will support distributed applications, highly available, highly scalable, distributed applications without a lot of the headaches of having to configure VMs and doing a lot of that kind of thing. So very much a realistic option here. Now, I did want to show you a brief demo of Kubernetes on Azure, just to show you that I have this exact same API that I had running here. Let me go over to the portal and I'll show you my little, what I did is I actually took my function app and I containerized it. And so instead of running my my application inside of a function app using Azure Functions, I actually created a instance of that. I took the function apps API and containerized that and deploy it as a container inside of Azure Kubernetes services. So this allows me to have the same code base. If I wanted to run serverlessly as a serverless option, I could, but I can also containerize it. And this allows me to run this on-prem and so on. So if I go to this endpoint right here, I have this running as a ingress controller. I'll show you the ingress controller in a minute. If I do that same API, multiply, that I have right here, this is running as a containerized Azure Functions implementation on Azure Kubernetes services. Now, you might ask why I would do that. It's basically just to show you that I can containerize a function app and deploy it on Kubernetes, and that's sometimes a viable option if you want to be able to move your function apps over to something like AWS, for instance, or you want to run it on premise, but you can also run it the same code base in an Azure function as well. And that's one way that people have done this. But in any case, to show you what the code looks like for this, let me pull up my ingress controller. Now, I'm not going to spend a lot of time explaining this to you, but I did want to show you the code that configures the ingress for this. And this is what I'm doing to configure my web service here. This is the ingress configuration for this. Basically, I'm just configuring Kubernetes to expose a container. And so this basically is using Kubernetes configuration files called manifest files. And I'm basically saying, listen at the root here, right here, and then I'm going to expose it on port 80. Here's a backend service that's using a load balancer. Take everything that comes in on port 80, forward it to this guy right here that's a load balancer for a bunch of backend containers that are deployed as a deployment. And it's deploying 3 instances of my microservice 3 instances of my microservice in the back end right here. And actually it's right there. That's the name of my container. Microservice like that. Now it's deploying 3 instances of it. So the service is doing a load balancing act on my backend service here, which is running a function app. And this is the ingress controller that's running as the front end for it. Now I can configure this ingress controller to do SSL offloading, a number of other features that are built into it, but that's just configuring Kubernetes. A lot more configuration here than what I would have to do for a function app if I was going to go that route. But in any case, it's pretty straightforward to set up Kubernetes to do microservices because it has a lot of the built-in plumbing though, and it's a well-documented experience, and a lot of folks have already plowed that row so that you can take advantage of a lot of the work that's already been done to get microservices running in a containerized environment. Now, I have a couple other environments that I want to talk about that I don't have demos for, but one of them is APIs and app services, and this is a traditional approach. This is something you can do. I'm not going to say that this is a best practice or even an advisable approach. However, if you have an old microservice suite that you're running on, say, something like IIS, and you want to just bring it to Azure in a more native fashion without having to do some refactoring into serverless, or you don't want to containerize it, but you have these APIs and you want to make them distributed in a way that is scalable, etc. You can take them, usually you can take them into app services without having to do a lot of work. Sometimes you might have to do some remediation to get them to work in app services, but you can do microservices with APIs on app services. However, it's not the serverless approach that we would typically appreciate for them. But in doing so, if you do implement APIs that are microservices that have traditionally run on IIS, you basically are responsible for doing the state management, a lot of the service discovery and the inter-process communication, and the security and the versioning and the data access, but you can take advantage of the platform for scaling high availability and configuration management, because those are kind of baked into Azure App Services. However, it's assuming that your APIs are going to do state management and appropriately do inter-service communication and security and versioning, etc. And you've designed your APIs to be a microservice rather than be a monolith in that respect. So it's assuming a lot that you're doing things correctly in your APIs. Now, this approach has been done, and a lot of folks do like it because it does give you a lot of versatility for taking something like an old monolith, breaking it up into microservices, and then deploying it to Azure App Services, and taking advantage of the platform as a service offering without having to use something like containers, or without having to go do as much development as you would if you went through a serverless approach. Serverless is going to force you to do better patterns, but it's not going to give you as much versatility as, say, something like an API would. So again, that is a possible option. Another one that I do want to mention here that is an out-of-the-box experience for microservices is Azure Service Fabric. Now, Azure Service Fabric is kind of a niche player in here because Azure Service Fabric can do microservices out of the box. Like serverless, it is an opinionated approach. It gives you a programming paradigm that you implement. And so it gives you, and so you program according to the programming paradigm, and then you take your application and deploy it to Azure Service Fabric. And then Azure Service Fabric will then just do a lot of the other kind of work, all the work for you. In fact, what Azure Service Fabric does really, really well if you implement it as a native application is it kind of takes care of all of this for you. Because it's purpose-built for microservices. You don't have to worry about scaling. That's handled out of the box. High availability out of the box. State management is out of the box. It's built into the distribution. Configuration is done out of the box. Service discovery is done through well-known hosts out of the box. Inter-service communication is secure out of the box. Security is done out of the box. And so all of these things are built into the platform. Versioning is done out of the box. The only thing it doesn't really do for you is external data access. And so if you use Service Fabric, you're going to get a lot of this out of the box. The one caveat of Service Fabric, though, that I would say is that the programming paradigms for this are very, very opinionated, meaning that you have to do things according to the patterns that it prescribes, or it doesn't work very well. And so Service Fabric is going to force you to do more microservices in a lot of ways. However, but you get a lot of advantages as a part of that. And that's basically why it forces you to do these patterns, is so that you can do microservices in a way that adopts the best patterns that Service Fabric prescribes according to the principles and patterns that it prescribes out of the box in the programming paradigms. So you can write .NET code in this. If you can write, and you can also write Java code in this. You can also run containers on Service Fabric, but it's more of a container orchestrator, so it would have more in common with something like Kubernetes in that respect. But if you go native Service Fabric, you're going to be doing microservices whether you like it or not, and that's just a part of the application suite there. So something to consider. If I was going to go head on into a microservice deployment, and I kind of knew fairly, if I knew right off what I was going to be writing for, and I kind of had a very well-defined set of specifications for my APIs, and I knew exactly what I was going to be writing, I might give Service Fabric a heavy consideration, and you might even do a POC against it to test it for greenfield site services for microservices, because in doing so, I'm going to be able to take advantage of a lot of these things that come out of the box without having to configure a lot of stuff like you do with Kubernetes, or with something like Serverless, which can do microservices, but it's not explicitly microservices. Service Fabric is, though, explicitly microservices out of the box. And then lastly, Azure VMs. Now, people might think of as, why in the world would I mention Azure VMs as a way to run microservices? That's because Azure under the hood with infrastructure as a service gives you a lot of tooling for doing a lot of the kinds of things that you would get out of a platform like Kubernetes or Service Fabric, but it requires a lot more thought and a lot more configuration put into the virtual machines than you would if you were doing something like Kubernetes, where it's just kind of does it for you, or Service Fabric, where it just does it for you. This requires a lot more of that configuration, but if you do it right, you can actually use VMs to do a lot of the kinds of things that you would do on some of these other platforms. And this is sometimes a good approach for folks that are coming off of an on-premise environment, already have microservices running there, but don't want to have to rewrite a bunch of code for a bunch of these other platforms, or don't want to deal with containerization. You can then go to Azure VMs. And Azure VMs, the reason I say they work for microservices is because with something like Azure VM scale sets, you can configure high availability and scaling. You can also do you can do high available. You can do inter-region high availability with the zone configurations with Azure VMs. You can do zone redundancy, and you can also do a lot of load balancing through Azure App Gateways and Azure Load Balancers for high availability and load balancing between these two. And it has things like health probes built into those platforms so that you can monitor the backend VMs for failure. You can do a lot of those kinds of things with a lot of the infrastructure as a service built into Azure. And so Azure App Service, Azure as application gateways, Azure Load Balancers, and Azure, even as something like Azure API Manager, can do a lot of those kinds of things for you. And so you can front end a lot of this with a lot of that infrastructure as a service and still get microservices running on Azure VMs, taking advantage of infrastructure as a service. But all these other kinds of things down here, it's not going to do as much of that for you, because VMs, again, require that you maintain the virtual machines. But not only that, you have to configure things for state management that requires some kind of caching service, or so configuring a load balancer to do something like sticky sessions. Configuration management, similar to that, it's not going to have a lot of that built in for you. You'd have to configure some kind of configuration management system, or use some kind of DevOps process to build that out. You also do service discovery, inter-service communication, security and versioning, and data access. All of these would have to be basically built by hand. So this would be one of those things that you would have to really consider what you're going to do if you're going to be going along those routes. So of the 5 options, just to recap, we have Azure VMs, Service Fabric, APIs and API management, containers on something like Kubernetes services, and functions. Now, all of these can do microservices, and they all have advantages and disadvantages, but they have different approaches, different programming paradigms, but they can all work for performing the same kind of task, and that is distributing a system of services that communicate over a network. And Azure has a lot of different options there for supporting that. Now, again, as I was going at this with Greenfield, I would probably go with Azure Functions kind of as my first choice. Service Fabric, I would give it a heavy consideration if I knew ahead of time what I was probably going to be building there, and might do a POC there. And if it works well, I might adopt that. Then I would probably go containers, and then I would probably go down the VM route or the API route last. So that's kind of what I would get at there. So that's my spiel on that. Here's a list of best practices. I've already said most of this. The only one I would probably call out is is adopt CQRS and for data access, and just make everything asynchronous. So any questions? I know we're a little bit over time. I do want to take time for questions here. If you have questions, please put those in the questions over here, and I will gladly answer those here. Let's see what we have here. First question is, all people present in the Microservice Architecture is a beautiful picture, interacts with A and B and C and D. How inefficient this works with REST is used for microservice purposes. I'm not sure I understand the question there, but basically the question is, the intent of the question is it efficient to work mainly with HTTP REST? No. Microservices can work across multiple platforms. It's not restricted to REST. It's not restricted, and like I said, there are multiple patterns for CQRS. CQRS being one of those, message buses being another. There's a lot of different patterns you can use for this, and it's not inefficient to use REST. It's just one of the many options you can use, so that is what we might consider there. So I think that's the only question that was asked. If there's no other questions being presented here, I think we'll call it a wrap. If you guys, if you don't have any other questions, I'll be glad to feel free to email me, or you can reach out to me on Twitter. I would glad to hear those if you have them. And thanks for coming out. Thanks for paying attention, and I hope to see you on future One Webinars.